Okay, so we're going to do parameterize a few more surfaces before we get into actually computing some integrals. We're going to kind of go through some of this quickly. So let's say that we want to parameterize the paraboloid. So the paraboloid, standard paraboloid, has the equation z is equal to x squared plus y squared. This is just the standard upward opening circular parabola. Well, so there's a lot of symmetry here. So there's a number of ways that we can think about this. One natural way is to think in terms of cylindrical coordinates. Okay, so in this case, z is equal to r squared, x is equal to r cosine theta, and y is equal to r sine theta. Z is equal to r squared because z is equal to x squared plus y squared, and r squared cosine squared plus r squared y squared is equal to r squared. So this is just the standard, all this is the standard cylindrical coordinate representation of a parabola. But we can use this to make a vector parameterization and say it's going to be r of theta r. So this r is different from this r. We just got to get used to that. And this is going to be r cosine theta, r sine theta, r squared, and here r, if we just want, well, r is going to go from 0 to positive infinity, but it doesn't really matter. It could go to negative infinity, and then if we want the whole paraboloid, theta is going to go in between 0 and 2 pi. Or we could do this in spherical coordinates. So let's change color. So red will mean spherical coordinates. So in spherical coordinates, z is going to be equal to rho squared sine squared phi. Why is that? Well, x in spherical coordinates, x is rho sine phi cosine theta, and y is equal to rho sine phi sine theta. Okay, and that is why you don't start an example before you know how to finish it. Sorry, you didn't get to see that, but I had to take a 5-minute pause to figure the rest of this out. Okay, so now this, z is in terms of rho and phi, x is in terms of rho, phi, and theta, y is in terms of rho, phi, and theta, but we need to reduce this to 2 parameters. So we need to somehow, in this case, we want to write rho as a function of phi and theta, or in this case, it's just going to be phi. Now, I can talk to you more about this later, but for now, you're just going to have to trust me that rho is equal to cosine phi over sine squared phi. This is actually an interesting exercise for you to be able to figure this out on your own, so go on ahead and do it. It might take you a while. So now the x coordinate is going to be, this is rho, so now where I see rho, I replace it with this, and what I get is the following. This is what you get. So this kind of much more complicated formula than what we had up there. Okay, but it's also nice because theta and phi are different parameters than r and sine, so it's a different way to express this same surface. And just to show you that I'm not pulling your leg, let's look at this. Okay, so here's a parameterization that I just gave you, and you can see that it is in fact a paraboloid. Okay, you can even play around with the grid lines. Okay. Okay, but another way to do this is the following. So let's just observe the fact that we are given z as a function of x and y. So in other words, we can use the x and y as parameters and use and z is just equal to x squared plus y squared. So we'll use green for this. So this would be r of xy is equal to x, y, x squared plus y squared. Okay, so which one of these parameterizations is the best? Well, let me just say one thing. This is very similar to, remember, if you wanted to find the vector parameterization for the graph of y is equal to f of x, remember the vector parameterization was just r of x is equal to x f of x, or really we used a different variable, r of t is equal to t f of t. And so if you want to use different variables other than x and y, you could say r of st is equal to st s squared plus t squared, but that's not necessary if you don't want to. Okay, so now the question to ask is, which one of these parameterizations is better? And the answer is, well, it depends on what you're going to do. When we start to do integrations, some of these are going to be easier to integrate. The formulas that are involved, some will be easier to integrate than the others. Each one of these has different advantages. Mostly when you try to say, what if I just want the part of the parabola going from this height to this height? Then this works very well because you can restrict the R parameter domain. Or let's say you just want the part of the paraboloid that lies above the first quadrant. This also works nicely because you can restrict the theta domain. Okay, but maybe these aren't easy. This isn't easy to integrate as the other one. So again, it just depends on what the application is. These are several different ways to give a vector parameterization for a paraboloid. Now we're going to look at a cone. Okay, so let's look at a cone. The parameterization for a cone, I'll just stick with green. So we'll look at the cone. Z is equal to 2 times the square root of x squared plus y squared. Let's get a few different parameterizations. So another way to write this is z squared is equal to 4x squared plus 4y squared. Now the first parameterization, the most obvious one, is just to use the fact that this is the graph of a function. And so we could say r of, I'll just stick with x and y as the parameters. This is x, y, 2 times the square root of x squared plus y squared. Now this is very good because you can just write it down directly. But if you want to sort of use properties of the cone that depend on its circularity or the symmetry with the circles and stuff, then maybe cylindrical coordinates are better. So in cylindrical coordinates, z is going to be equal to 2 times r. Why is that? X squared plus y squared is r in cylindrical coordinates, and x is r cosine theta, y is r sine theta, and so the parameterization is going to be r of theta r is equal to r cosine theta, r sine theta to r. Okay, and finally, another kind of reasonable choice would be to use spherical coordinates. So now spherical coordinates get a little more tricky. So in spherical coordinates, what does this equation become? Well, it says that z is equal to 2 rho sine phi. And also remember that z we can write in spherical coordinates as well. So this says that rho cosine phi is equal to 2 rho sine phi. In other words, tangent of phi is equal to 1/2. Okay, so tangent of phi is equal to 1/2, so this means phi is arctangent of 1/2. So this means that phi is roughly equal to 0.43. Okay, so now the parameterization in spherical coordinates. So we're going to use phi and theta as the parameters. R of phi theta. This, well, x is rho, so this is rho times sine phi times cosine theta. So this is going to be sine 0.43 cosine theta. Okay, then this is going to be rho sine 0.43 cosine theta. And now lastly, it's going to be the z coordinate, which is 2 rho cosine phi, which is cosine of 0.43. But let's just, so what this here says is that cosine phi is equal to 2 times sine phi. So it's going to be better if we just write it instead of cosine phi. It's going to be better if we just write 2 sine of 0.43. Okay, it's going to be a little bit, it's going to look a little nicer if you try to graph this in GeoGebra, and I'll let you think about why that is. Anyway, so these are 3 different vector parameterizations of a cone. Probably the two best ones in some sense, my guess, are going to be the one where you just use the fact that it is the graph of a function and you can write it this way, and the other one is probably the next best one is going to be cylindrical coordinates. Actually, these two are probably equal just based on what you need to do. So let me just say one more thing. Just I've used this fact, but I want to say it. If z equals f of xy for xy lying in some parameter domain is a surface, then this vector parameterization this vector equation or vector formula is a vector parameterization for the surface. So if you're given a surface as a graph of a function, this is kind of the most straightforward way to write down the parameterization. Sometimes it'll be the most useful one. Sometimes there might be another one. You just kind of have to, just sort of depends on what you're trying to do. Now, I would like to say more, but I'm going to go meet William and Ezra, Jonathan for lunch. So see you later.